Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will continue the discussion of wave propagation inside a good conductor. By good conductor, we mean that the conductivity of the material or the conducting material is much larger than the product omega epsilon, where epsilon is the permittivity of the material and omega is the given frequency of the wave that is propagating inside the conductor. We will touch upon a very practical and important topic of skin effect, which tells us under high frequency conditions what will happen to the current flow inside these conductors, whether the current will be uniformly distributed throughout the conducting medium or whether it would be not uniformly distributed throughout the conducting medium. This has practical importance because if you are designing systems at very high frequencies, you would want to know what is the current flow inside the conductor so that you can actually use the right amount of conductor. If for example the conductor seems to have been there flowing entirely near the boundary, then there is no point in having a 10 meter thick conducting wire because most of that conducting material will not carry any current. However, if it turns out that the current is uniform, so then the entire 10 meters of thickness of the conductor will carry current and therefore you do not have any savings on the conducting material. Okay. So that is determined by what is called a skin effect, and we will talk about skin effect. We have already talked about how a wave would propagate inside a material which is a good conductor, right. We have seen what will happen to once you start from Maxwell's equation, what will happen to the propagation coefficients. The propagation coefficient will turn out to be complex, with the real part having the attenuation component and the imaginary part having the phase coefficient, right. So just to refresh your memory, in the case of a good conductor material propagating inside in general a conductor first, then the propagation constant gamma will become, or the propagation coefficient gamma will become complex. It is given by square root of j omega mu sigma plus j omega epsilon. If you split this itself into its real and imaginary components, you will obtain some alpha and beta, where alpha will be the real part of gamma and then beta will be the imaginary part of gamma. This alpha tells you how the waves are attenuating, because we have assumed that the waves as they propagate along the z axis will propagate as e to the power minus gamma z. Okay. So in place of gamma, if you now substitute for alpha and beta, you will have e to the power minus alpha z and e power minus j beta z. This factor we already know simply allows you to determine what is the phase delay that is the wave is experiencing with respect to a certain reference phase, whereas e to the power minus alpha z corresponds to the attenuating factor. The amplitude of the electric field or the magnetic field attenuates as the wave propagates inside the conducting material. Okay. For the case of a very good conductor, sigma is much larger than omega epsilon, therefore gamma can be rewritten as j omega, approximately can be written as j omega mu sigma, and we have already shown that this can further be written as 1 plus j divided by root 2 into square root of omega mu sigma. We also denoted by the variable delta, okay, we denoted this variable delta as square root of 2 by omega mu sigma, therefore gamma is equal to 1 plus j into delta, okay, sorry 1 plus j divided by delta, okay, which indicates that alpha is 1 by delta and beta is also equal to 1 by delta. Okay. So the wave experiences phase shift as well as the wave experiences attenuation. Now consider this kind of a scenario where we assume that the direction of the wave propagation is along z axis and we take this one to be the x axis, and we have this plane which extends all the way from minus infinity to plus infinity, but this is located at z equal to 0, separating two regions. Below this z equal to 0, the entire medium below this particular plane is made out of a good conductor. Okay. So this entire thing is made out of a good conductor where sigma is much larger than omega epsilon, and above is a perfectly insulating material. As an example, we will simply take this one to be air. Now, when there is a plane wave propagating, so it has a certain electric field component and the direction of propagation which is along the z axis. So, the wave has an electric field which we will assume to be having the x component. Clearly, the magnetic field would then be along the y component, correct. So, the pair Ex and Hy will have a certain ratio of the medium impedance inside the air. Okay. Now, imagine this wave steadily approaches the interface, and at some particular time, which we do not really worry about at what time this happens, because we are only going to look at the steady state, we have the situation that the electric field or the wave has actually landed and is now incident on the conducting boundary. So, at z equal to 0, any value of z below or greater than z equal to 0, right, will then be completely a conducting surface. And on that conducting surface, the electric field is oriented along the x direction, the magnetic field is oriented along the y direction. The wave has now incident on the conductor. At the surface, we will assume that the amplitude of the electric field is given by E0, okay, and the amplitude of the magnetic field is given by H0. Please note that we are only considering a good conductor. We do not let sigma go to infinity at this point, which represents a perfect conductor. Okay, we do not have a perfect conducting situation here. We have an imperfect conductor, but that imperfect conductor is also a very good conductor in the sense that its sigma is much larger than omega epsilon. Now, what really happens in this case? Well, you should first of all raise an objection saying that we have not really considered the scenario where a plane wave is impinging on another conducting material and what happens as a result of that. You will be right, we have not really addressed the situation of what happens when a plane wave hits a particular medium and what changes happen inside the first medium and inside the second medium as such. Okay. But we will disregard that problem because we are not really looking at what is happening to the medium or the fields inside the medium in the air side. We are interested in what is happening once the plane wave hits and has a value of the electric field at the surface as E0 and the magnetic field as H0. What happens once that wave starts to propagate inside the conducting medium? Of course, you know that that wave has to decay in amplitude. Okay. Now, let me show you what is kind of the picture that I want you to carry forward for the next few minutes, so that you really understand and appreciate what is happening to the skin effect. Imagine that this is the conducting media. Of course, this should exist all the way to infinity and all the way to infinity. This medium is air and the wave now the wave is now incident and lands on this conducting media. So, this surface which you can see on the top will separate the media air and conducting material below. So, all this wooden block, you can think of this as comprising of the conducting material. Now, what is the direction of the electric field on this surface? Well, the direction of the electric field is along the x direction. So, this is the x direction of the electric field that we have, which is indicated by my fingers pointing to that. You can't really see, but my thumb, or now you can see, the thumb indicates the direction of propagation. Okay. So, on the surface, these, of course, my fingers are not uniform, but you have to assume that all the fingers should have the same length because you are actually looking at a uniform electric field. The electric field amplitude does not depend on the value of x. Okay. So, on the surface it has a constant value of E naught. Now, what happens as this wave begins to propagate? Well, you can imagine that as the wave begins to propagate, because of skin effect, the amplitude of the electric field starts to reduce as a function of z, right. So, it goes as exponential of minus z by delta. So, this is the length on the surface, the length reduces, reduces, eventually tracing an exponential decay. At infinity, the amplitude would be equal to 0. So, this is all the electric field. Now, in a conducting material, the relationship between electric field E, the conductivity of the material sigma, and the current density J is well known. This is the point form of Ohm's law that we already know. J equals sigma times E. So, if this is the variation of the electric field inside the material, so should be the variation of the current density J. On the surface you have the current density J0, which is given by sigma times E0, and this J vector or the amplitude of the J vector starts to reduce, eventually going towards to 0 at Z equal to infinity. Okay. This was all about electric field. What about the magnetic field? Now magnetic field will be along the y axis. So in this case assume that they are coming towards you as you look at the screen. So this is how on the surface you have a uniform magnetic field H0, and then this reduces in amplitude as it goes down and eventually goes off to 0. So at Z equal to infinity you do not have an electric field, you do not have a magnetic field, nor you have the current density, because all the amplitudes of these quantities have gone down to 0. Now if I ask you what is the total current that is passing through a particular plane, which I will obtain by cutting through this material in this way. So you have to imagine that I am cutting the material through this way and exposing this particular cross section. Okay. Along y I go a certain distance w. Okay. So maybe this is y equal to 0 where the point I am showing, this is y equal to w, and then you take this edge, you keep going inside, right, inside the conducting material, you go all the way to infinity, come back up parallel to this loop or to this line, and then come back onto this edge to meet back at the surface. Okay. So along Z you go to infinity, then go along minus y direction, then come back and then do this. Now clearly there has to be some amount of current that is flowing through this open surface, because my J vectors are all crossing this. Okay. On the surface the J vectors are uniform, but then they reduce as you go down to the conductor. Let us calculate what is the amount of that current that is obtained by cutting the plane. So I will show you kind of a way to this is the loop that I have drawn, and I have actually illustrated that one to you by this example of the duster. Okay. We call this loop, let us say we name this loop as A B C D A. Okay. The J vectors are all coming out perpendicular to this loop, because the J vectors are all along the x axis, and while these are the J vectors that come out on the surface, they are uniform, but as you keep going inside the conducting material you will see that they are all coming, but then the amplitude actually starts to decay exponentially. So the amplitude is decaying exponentially. So what is the total current enclosed? Well, the total current that is enclosed over the loop A B C D A will be integral over 0 to w, because I have assumed that along the y direction we have taken a distance of w, along z we have taken all the way from 0 to infinity, right, and the way the current density would be varying with respect to z, dz dy. Here the J vectors are all independent of y, therefore there is no problem of simply removing the integration with respect to y. So with respect to y what would happen? It would get multiplied by w, and here you have 0 to infinity j of z dz. What then should be j of z? Well, we know that j of z, the way the current density would change with respect to z, is given by sigma times E of z, and we know that electric field is along the x direction, but its amplitude is z dependent, and this is going as sigma E0, which is the amplitude at the surface, and e to the power 1 plus j minus 1 plus j z divided by delta, right, where alpha is equal to 1 by delta, beta is equal to 1 by delta. So here you have e power minus gamma z, and that is essentially what I have written. If you now put this one back into the expression and carry out the integration, I will leave this as an exercise, you do not get infinity, okay, because the amplitude keeps on reducing. Although the loop area seems to be infinity, and in fact it is infinity, the total current carried by that open loop ABCDA is finite, and you carry out this integration, you will see that this will be given by sigma E0 divided by 1 plus j times delta. So did we get this one correctly? Yeah. So this is the total current that is enclosed by putting this j of z back into this one. Sorry, this is multiplied by w actually. So you get w sigma E0 delta by 1 plus j. Now I can, instead of writing this W here, I will do a small trick. I will multiply W with delta, or I put W and delta together, and I still have my sigma E naught divided by 1 plus J. Okay. Now look at this term W into J. Okay. What is the units of W? Well, W is the distance unit, so it is measured in meters. What is the units of delta? Delta again has to be measured in meters. Why? Because you have e power minus z by delta. Z is in meters, therefore delta also has to be in meters. Okay. So you have this also, delta measured in terms of meters. So what will happen when you take the product of these two? This will give you meter square. And what is the units of meter square, or what is the quantity which has a units of meter square? That is area. Correct? Area has meter square. What is this area? This area has a width of W along the y axis, and along the z axis it is not infinity, but the z axis width is just about delta. Okay. And if you know, or you already know, that this sigma E0 is the current density J0, which can now be considered to be uniform over this cross section. So over the cross section, which is W wide and delta thick, you can assume that the current density passing through perpendicular is uniform and has a value of J0. But if you really want it, you can also consider this to be a complex J0 by 1 plus J. But otherwise the point is that over this cross sectional region, the J vector is uniform, or you can think of this current coming off as a result of the uniform current flowing only in this thickness, rather than the current that actually obtained by going all the way to infinity coming back, right. So this was the original loop that we had considered, but rather than finding this original loop where the current is changing exponentially, you can obtain the same value of the current if you assume that entire current flows only in this small cross section of thickness delta and a width W. In fact, one also defines sometimes what is the current per width. Okay. Please remember, current per width must be taken along the y axis. Okay. So current per width is given by the total current enclosed by the loop divided by W, and obviously this can be obtained from the above equation, or from this equation, by simply dividing this one by W. Let us not complete our analysis yet. Let us go back to this example that we have talked about. Okay. Now notice that we had considered this cross section, right. So we had considered this cross section. Now instead of considering that cross section, let me move a distance L along the surface of this particular interface, right. So on the interface I move along a distance of L, then I move a distance of W, then go back by moving a distance of L, and then come back to the starting point. Okay. So I move from here to here, then go along the direction of W, then come back and then go back, right. So I actually form a loop, right. Now on this loop, now if I ask you, on this loop, if I just consider these two planes, okay, so this plane is at some, say, x equal to 0, and this plane is at some x equal to L, okay, what is the potential difference between these two planes? The potential difference between these two planes must be given by the integration of the electric field along the length L, correct. So on this plane and this plane, the potential difference between these two planes is integral of electric field along the length L. But luckily for us, this electric field is uniform on the surface, has a value of E0, the length is L, and E is along the x axis, integration is also along the x axis. Therefore E dot dl, which defines my EMF, will simply be given by E0 into L, correct. Now E0 into L is the potential difference that I see on the surface. If I now consider the ratio of potential difference to the current enclosed, okay, what do I get? I know what is the current enclosed. This I know from the previous expression given by W delta sigma E0 by 1 plus J. So I need to go back and put that expression into this. I get 1 plus J divided by W delta sigma E0, okay, times E0 into L. Clearly E0 cancels on both sides, so I can remove E0 from the equation. So E0 is cancelled on both sides. So what I obtain is 1 plus j divided by W delta sigma, or rather I will rearrange this one. So let me say 1 plus j by sigma delta L by W. Okay. And what is the ratio of voltage to the current, potential difference to the current? This has to be the impedance, and in this case the impedance turns out to be complex, right. So in this case the impedance turns out to be complex, but notice we are not done yet. So notice one thing, suppose we consider L equal to W, that is we consider the potential difference between two planes which are W apart and the current per width, or the total current of the same width W, right. So if I consider that one and then take the ratio, since L is equal to W, this quantity will be equal to 1, and what I obtain is a complex quantity 1 plus j by delta sigma, and this is called as the square resistance. And this square resistance is very important in VLSI or microelectronics areas, where you can actually calculate the resistance or the complex impedance of the materials, of the materials or the interconnects by this idea. So you divide whatever the overall region where you are computing the impedance into small squares, and of each, of course they are all squares. So on each square you calculate what is the impedance and then put them together in order to form the overall impedance. We are not yet done. This impedance that we have defined is defined by the potential difference to the current enclosed, right. There is another impedance which also turns out to be complex in this case. This is called as the surface impedance. Okay. This surface impedance is defined as the field amplitude to the total current enclosed. Okay. So it is not the potential difference, but it is the field quantity. So E0 divided by I enclosed, and this will be equal to 1 plus j divided by, now because there is a E0 on the top here, W delta sigma here, this is times E0 is also present. So this, luckily again E0 cancels on both sides, and the surface impedance that I obtain can be thought of as having two components, that is the real part and the imaginary part. We will denote the real part as R int, which will be the resistive part, and the reactive part by X int, which of course is a function of frequency, right. So this will be equal to 1 plus j divided by W delta sigma. Okay. So where again you can rewrite this one, this is 1 by W delta sigma plus j by W delta sigma. Okay. What is this W into delta? This is area, and then you have 1 by sigma times area, right. So 1 by sigma times area is resistance by L of a long tube which has an area of A, right. The resistance of such a tube, as you know, is given by L by sigma A, or resistivity or resistance of that one is given by L by sigma A. So this component R int can be thought of as resistance per unit length. Similarly, X int will be equal to 1 by W delta sigma, and X int is equal to omega times. So X int, let us write it over here. So X int is equal to 1 by W delta sigma, again W into delta is the area, right. But X int can be written as omega into L int, where L is the inductance. It is not actually an inductance that is there, but it kind of an inductive reactance. Okay. So this inductive reactance and has a certain inductance associated with that one, and that equivalent inductance L int will be given by 1 by, so L int will be given by 1 by W into delta, which is the area, sigma omega. Okay. So this is the inductive component. So what I am trying to tell you is that if I consider a good conductor and have some way of inducing a current, either it could be a plane wave that has been applied, or I have actually taken this piece of conductor and applied a potential difference, right. I can apply a potential difference on the conductor between two planes now, right, and those two planes will not be at the same potential, because this is not the time invariant or the static case. This is a case where there is time variance in the form of a sinusoidal variation. So if I induce a potential difference and cause a current to flow, this current effectively flows only through this small thickness. So you can imagine again to this one that if you take this dusting part thickness as delta, right, the current does not really go all the way through the infinity. you can imagine that most of the current or the effective current is lying only in this small patch of thickness delta. Okay. So, the phenomenon in which the current actually starts to flow very close to the surface, just below the surface and over a thickness of delta, is called as skin effect, and this is an important artifact or an important effect in high frequency systems. We will not leave the skin effect at this point. We will go to an even more interesting way of the skin effect by calculating what is the skin effect in a different structure, which is again very important practically, and that structure is a simple round wire. Okay. So, we imagine that there is a round wire. Okay. So, I have a wire of some radius a here. Okay. This is made out of a good conductor again. So, I will not write it here, but this is made out of a good conductor. Okay. And what I want to find is what is the skin effect, what is the surface impedance, would it be the same as the previous case, would it be different from this case? Well, before we can even answer these questions, we have to understand something that is slightly important. We have not really talked about the fields inside a wire. We have not even talked about the fields inside a wire when we are in, we have talked about the fields in a wire only for the static case, and we have calculated the inductance of this single wire, right. So, which we computed to be something like mu by 8 pi. You know, in the coaxial case that we had computed, there was an inductance corresponding to the inner tube which was carrying a current I, and this current I was a static current at that time. The corresponding inductance contribution was mu by 8 pi. We have already seen this one. However, what happens when the current is varying with time and the frequency is very high? You can again imagine that most of the current will then be flowing in the thickness of delta. Okay. So, there will be essentially approximately no current here, but because most of the current and almost the entire current is kind of concentrated on the thickness of delta near the boundary of this wire. Okay. But what is the value of that? How do we calculate that? These are not simple to calculate from the plane wave analysis that we have done. So, we will do a slightly more rigorous analysis wherein we will employ the quasi-static analysis by employing Ampere's law and Faraday's law, and we will see how the fields inside a wire, okay, or how the current distribution inside a wire can give rise to skin effect. So, we will consider this quasi-static analysis of the wire in the next module. Thank you very much.